is equal to 5. So my samples would probably distribute themselves pretty much like this. This would be 2 standard deviations to the left, 2 standard deviations to the right. You can read that that's 90 and that's 110. Okay, so now let's say that given this population, the way that this population, I'm assuming that this is the way this particular population, if I took a sample of size 25 over and over and over again, this is the way that the samples would distribute themselves according to this standard error. Okay, so now let's say that I want to compare this population, which I believe that population, I think that this population has a mean of 110. Let's say that I want to compare it to a population that I believe, again, this is a population that I believe has a standard deviation of, a mean rather of 100, to a population that has a mean of 120. And it has approximately the same standard deviation as this one does. Well, let me change that. Let me make that 115. Okay, well, what would that other population, if I took repeated samples of size 25, what would that other population look like? Well, first of all, its mean would be at 115, the repeated samples at the same size, right? And it would extend 2 standard deviations away. If it had the same standard deviation, same sample size, it would extend down to 105 for 95%. So it would look something like, right? It would look something like this other population, right? With the mean at 115. Okay, so you guys, let me just ask you quickly. If you have a question about that, ask me now. I have 2 populations. I believe I believe that one population has a mean of 100 and the other population has a mean of 115. I'm starting off with that belief, okay, based on other research that I've done, based on other studies, and so on and so forth. But now I want to prove that these are really 2 different populations and not the same population, that difference is real. Everybody kind of get that idea? Okay, I'll rewrite the writing on the left. Okay, my sample size was 25. My standard deviation was 25. My mean for this first population is 100. And my standard error comes out to be, I calculated, it's 25 over the square root of the sample size 5. My standard error is equal to 5. So this blue part represents the way that samples from this population has a standard deviation of 25 and a mean of 100, that this is what repeated samples out of that population might look like. Okay, so now I want to prove that it's different from this other population, where I believe the mean of this population is equal to 115. Okay, and I'm going to assume same standard deviation, same standard error, and so on and so forth. So now, if this population, if I drew, like I drew the blue here, if I drew a distribution that represented all the possible samples of size 25 for this population, it would be represented by a distribution that looked like this dotted line, right? It would extend over this other population, right? Or the samples for this other population. So now let's say that I took this sample, I took a sample from this population, and indeed my sample came out. I took 25 people. I got an average of 100. My so on and so forth. And let's say I did this, and this is my distribution. I'm backing up. Let me back up a second. Let's say I took a new sample from this population here. This population sample that I took was a sample size 25. How large a number would I have to get to prove that it's different than 100? Right? What would the average for this sample that I took from this population, how big would it have to be for me to say it's different than this blue population? Well, let's think about that. we would have to be, before we would reject the null hypothesis, in other words, with alpha is equal to 0.05, before we would reject the null hypothesis, we would have to be so far away from 100 when we took this sample that we would get this outcome only 0.025% at a time, 2.5% at a time. So I would need a difference between these two values of, of at least two standard errors apart, right? Depending on the sample size, the t-score, and so on and so forth, right? So these would have to be. I'm gonna assume, for instance, I'm gonna assume for starters that we know the population standard. I want to work with z instead of t. I would have chosen a bigger. Would have been better if I chose a bigger sample size. But I'm going to assume for a second that I'm okay with that, and I'm going to use z. What would this z-score have to be for me to reject the null hypothesis that mean for group 1 is equal to mean from group 2? Well, that z-score would have to be 1.96, right? So in other words, let me think about this. The z-score that I would need is going to be equal to 100, is going to be equal to whatever mean I get here, right? X minus 100 over my standard error, which I know is 5, right? So I can calculate my z-score has to be equal to 1.96 in order for me to say that these two populations are different. Because if my z-score, yeah, if I got 111 here, I would be over here. So 111 minus 110 over 5 is going to be bigger than 1.96. So I've satisfied the criteria that I need. Okay, the minimum number, the exact number that I need to know that there's less than 5% chance of my being wrong if I double-sided. Remember, I'm going to use 0.025 because I happen to be on this side right now. My minimum z-score is going to have to be 1.96. So now, okay, so now if I look at this, if these two populations really are different like this, let's look at from the perspective of this other population. What percentage of the time, if I took a sample of size 25, what percentage of the time would I get a value that's less than that 110, the number that I need to reject the null hypothesis for this population to be the same as this population? How often would that happen? Well, let's see. If I get this, my alpha error here is 0.05. But if I look at this population, if this is really the way that these two things are distributed with this variability and with these two means, these two populations, how often would it occur that I got a value less than 110 here for this population? Well, let's see what that would be. Z is going to be equal to, let's see, 110 minus 115 over the standard error, which is 5. That's equal to 1, right? Well, we know one standard deviation, that leaves this area is about 16%. So given this circumstance, given that the sample size is only 25, right? And that the means are only 15 apart. If I took a sample from this population, here, 16% of the time, I would get a value that's under 110. Well, what does that mean to me? What that means to me is when I sample 25 people from this population, and I want to be less than 5% chance of being wrong if I reject my null hypothesis, I need to get a value higher than 110, right? That's my alpha error is 5%. However, well, gee, look at this. 16% of the time, I'm going to get a value that's less than 110. So 16% of the time, I'm going to fail to reject my null hypothesis, even though the two means really are different. Okay, so now, I have my alpha error is 0.05. So when my alpha error is 0.05, I have a 16% chance of failing to reject the null hypothesis. Okay, so now that means that I'm going to look at this as a single-sided test for our purposes. That means that I have a good chance of failing to reject the null hypothesis when indeed they really are different. That quantized, that's 16%. Well, let's say that I want to make less likely that that's going to occur. Well, one of the ways that I can make it less likely that's going to occur is to say, well, I don't have to be 95% sure. I can make my alpha, I can be 90% sure and make my alpha zero point 0.1 instead. So zero point 0.1 would be an area of 0.05, would move us over to here. So the probability of being wrong if I reject my null hypothesis now is 5% at the top. It moved this to the left. So the probability I would get out of this population a mean out of a sample of 25 that's less than what I need to reject is smaller than it was before, smaller than 16%. So one way I can reduce my chances of not rejecting the null hypothesis when I should, my beta error, right, is by reducing my alpha error. Increasing my alpha error makes it more likely I'll get a sample that is less than what I need to reject. Okay, that's really what this idea of beta error and alpha error is all about. Well, my chances of failing to reject is 16%. My chances of rejecting correctly is going to be like 84%. This is called our power. 1 minus your beta error is called your power. So in other words, the less area here where we would fail to reject the null hypothesis, the more power you have in this calculation. The more likely you are to get the right result and not fail to reject the null hypothesis when you should be rejecting the null hypothesis. Okay, so now we're gonna complicate. How else would I? Can anybody suggest to me another way that I would reduce my beta error or my chances of failing to reject the null hypothesis if I want my alpha error to be 1.96? How else might I do that? Anybody want to suggest a method of doing that? Increase the sample size. Perfect. Okay, and how does increasing the sample size affect us? Increasing the sample size narrows both of these. This one now becomes, they're still going to be around. They're still going to be around their own means, but now this is going to be narrower, and this is going to be narrower. So there's going to be less overlap between the two of them, reducing the chance increasing the chance that you'll be able to reject the null hypothesis, also reducing the chance that we'll fail to reject, even though the two means are different. Now, let's talk about calculating sample size. Okay. Now, let me see if I can erase some of this stuff, some of this nasty stuff. Let's see. I'm gonna redraw this. I think that's going to be better than trying to. Okay. Okay. Let me enlarge this. Okay, let's talk about sample size now. Okay, again, this was 115. I'm going to stick with the situation we had before. It's going to overlap to here. It looks something like this. Okay, let's talk about sample size. In order to reject my null hypothesis, I have to be 2 standard deviations away from my mean here. So my z-score, z is equal to, my z-score is going to be equal to 100, 110 minus 100. Oh, actually, hang on a second. Let me rephrase that. I have to have a z-score. Let me undo. That's good enough. Okay, my z-score, for whatever value this is, not really 110, might be something different. My z-score has to be equal to 1.96 in order to reject my null hypothesis, right? So I need a z of 1.96. So in order for me to get a z of 1.96, I have to have whatever value this is here, it has to be big enough that I get a z of 1.96. We know by looking at this that it's around 110, but it's not exact. If my standard deviation is 5, my standard error is 5, as I calculated before. My standard error is 5. We know that this value has to be somewhere around 110, not exactly 110. I don't know what that number is. I'm going to assume I don't know what that number is. So in order to reject the null hypothesis, I have to have a z-score of 1.96. Okay, well, that's pretty good. So now, if I want a beta error, let's say I'm willing to accept 5% chance of failing to reject the null hypothesis, right? So I want a beta score that's going to give me 5% of the population, that this area here is only going to be 5%. 5% chance of failing to reject the null hypothesis, even though that they're different. So I want that area to be only 5%. Well, now I need to use what would be the z-score that I need for this population to get an area there of 5%. The z-score I need there is 1.64, right? Or 1.68? I forget. I'm going to use 1.64 for now. You can look it up later on. So that I'm using the same x. I'm looking for the same number here. So I'm going to say x minus, well, in this case, it's 115 over the same standard deviation, I'm assuming same standard error for both groups, over 5. Okay, well, how did I get that 5? That 5 was actually the standard deviation of the population, right? That 5 was equal to the standard deviation of the population, that standard error, right, was equal to the standard deviation of the population over the square root of the sample size, right? Well, the standard deviation that I used before to get that, remember, it's 25. Sample size before was 25. I don't know what the sample size is now. So it's 25 over whatever the square root of the sample size is supposed to be, right? So instead of putting a 5 down there, because that's what the previous example was, we don't know what the sample size is that we need. That's the reason why we're doing this. I'm going to put the standard deviation over the square root of n, 25 over the square root of the sample size. Okay, I'm going to do the same thing here, 25 over the square root of the sample size. Okay, you guys see how I put that, why I'm putting that down there? This represents the standard error that we would get for different sample sizes. If this was a big N, well then X could be a different number. If this were a small N, then X could be another. If this is a big N, right? Well, then that big N makes this a small number, makes this a bigger z-score. So X can be a smaller difference. If it's a small N, then X has to be a bigger difference in order for me to get 1.96. So I substituted here the standard error based on the standard deviation of the populations or on my samples. Okay, so now I have two formulas here. Both these X's are the same number. Okay, and the only thing that is really different here is that we need to know what sample size that I need so that we satisfy both this requirement that I reject the null hypothesis at 2.5% in the upper tail, and that I fail to reject the null hypothesis 5%, less than 5% at a time, and satisfy that z-score for my beta error. Okay, so now what I do now is I solve for x in both cases, or at least in one case. So I'm gonna solve for x here. X is equal to, let's see, how am I going to do this? This, I can invert this and bring it up to the top. Where am I going to write here? 1.96 equals x minus 100, right, times square root of n over 25, right? You can invert and multiply. What's a better way to do this? Oh, actually, what might have been a better thing to do is just cross multiply. Let's cross multiply. Okay, I'm going to cross multiply here, and I'm going to say 1.96 times 25 over the square root of n equals x minus 100. Okay, bring that 100 over the other side. It's plus 100. Okay, and that's what x is equal to. Well, now I can substitute what x is equal to into this formula, right? Take all of this, substitute it for what x is, and I can eventually solve, after much torturous calculations in algebra, solve for n. And n will give me the sample size. I think we have a worked out version of this in one of the problems. Let me see. Let me see. Da-da. I stopped here because it was homework for. I stopped here. I think on Blackboard right now, there is a worked out version of this sample size calculation. I'm going to leave that to you guys to, you know what I'll do? If it isn't there, I will post a problem 14 is a similar problem to this, and the last part of it asks you to calculate the sample size. I'm going to post an actual completed version of a sample size calculation so that you can see how you would determine what the sample size has to be. Okay, so I'm not going to have time to do it right now because I want to cover one more thing. Okay, you guys okay so far? Did that help you at all in interpreting beta and alpha and so on and so forth? Those of you that are still that have managed to survive this so far, did that help at all? Okay, right. So you get the idea of this beta and this alpha and how it's dependent on sample size. I think you can. I think you should be able to use Excel. Worst comes to worst, you can copy and paste in your progression in Excel, right? So yeah, I would think this would be a lot easier to deal with doing all these calculations using it. I frequently use Excel in place of a handheld calculator. You should bring a calculator with you though when you come to the exam. And I don't think there's a function specifically for sample size calculation in Excel. I'll have to check that. I'll take a look at it this afternoon. Okay, finally, I want to just end with one more thing, and that's with Excel, with SPSS. And I'm going to have to do that very, very briefly. Okay, and I just want to show you that should you be given data that requires it, SPSS is going to give you a lot of flexibility in terms of calculating confidence intervals and performing t-tests of various kinds. So I can't find a recently used data. Let's use that. Oh, couldn't find it. Okay, I'll pull this one up. Okay, we have various kinds of data here. One of them is gender. I'm going to take advantage of gender just for no other reason, that it gives me a chance to get two different groups. Okay, in SPSS, when we want to do a variety of tests involving confidence interval and t-tests, we just simply go up to Analyze. I'm going to Analyze, and if I want to do confidence intervals, I can just go into Descriptive Statistics and go into Explore. Pretty much you can dispose of frequency and descriptives. Most of what you're going to want to do, you can do with Explore. Let's say that I want to calculate the age of the mother, which is a continuous variable, and I want that broken down by the sex of the child. I don't really expect there to be a difference, but this is going to break up. It's going to calculate the statistics for the age of the mother and separate it into two groups: male baby, female baby. So statistics is going to do 95% confidence interval, and I'm going to say okay. And indeed, it does the calculation for us. And you'll notice that the mean age of the mother for male children is 26, 27, and the mean age for female children is basically about the same thing. But it does calculate confidence interval, 26.36 to 27.55, and 26.27 to 27.48. So it automatically calculates your confidence interval. Notice it calculated the standard error on the way to doing that. Okay, so now let's say, and you can calculate confidence intervals using this if you have a large data set. I don't close this. Okay, so now I'm going to do something similar, except I'm going to do a t-test. I'm going to compare means, right? That's what a t-test does, is compare means. So analyze, compare means. Okay, a one sample t-test would suggest, okay, let's take the age of the mothers and compare it to, in this study, compare it to the value 30. Okay, is it different than a group that I know their population mean is 30? And we can go ahead and calculate that. And sure enough, it does a t-test, and it finds that the probability, significance is really a p-value, two-tailed. It tells you that the probability is very, very low that that these are from that this population would be the same as a population that has a average age of 30. Okay, so we reject the null hypothesis that our population is equal to 30. Okay, so next I might try analyze descriptive statistics, means, compare means, independent samples t-test. Well, independent samples t-test, I'm going to take the age of the mother again, okay, and I'm going to take a grouping variable for the, let's say, the sex of the child, okay, and in here you're going to have to actually define what the groups are. Say, I'm going to assume for a second 0 and 1. Okay, and say okay, and it'll actually do a t-test to compare the two of these. Nope, I got that wrong. Analyze, compare means, independent samples t-test. I'm guessing I got my variables wrong. Let's say it's 1 and 2 for male and female. Guessed wrong. See if it works this time. That worked this time. Now let's take a look at this. Now, notice that the standard deviations of the two groups are very similar. Well, since they're very similar and one's not double the other, we're going to use equal variance as assumed. So we're going to look at this table, going to go across this top row, came with a t-value of 0.19. That has a p-value of 0.84, far above our 0.05, which we need to reject the null hypothesis. So in this case, we can't say that the age of the mother for males versus female children is different. Two samples. You had two samples. One sample was the mothers of male children and the mothers of female children. So if we wanted to do independent samples t-tests, that would allow us to, that would allow us to automatically deal with both in the output, deal with equal variance is assumed and equal variance is not assumed. So you wouldn't have to choose which formula that you're going to apply. Just make a judgment about the actual standard deviations of the two populations. Finally, there is you can do paired samples t-tests. Okay, in a paired sample t-test, you would choose the two variables. I don't have one here that's available right in this data set. You would choose, say, the blood pressure before, blood pressure after for each same individual. Click OK, and it would do a t-test for comparing the differences in your before and after for each one of your people in your survey. Okay, so my voice is going, so I think this is a good time to end. We covered a lot of stuff very fast, and I can see that I lost a few people along the way, but most of you were able to stick around. A lot of you were able to stick around to the end, and some of you even were able to stay awake to listen to me droning on about this. But hopefully that'll clarify some things and help you out tomorrow on the test. And good luck on the exam. And spend a little time studying, going through the PowerPoints and stuff like that, and practicing a few of these. And like I said, I'll post something. The calculation shows the sample size later on. Yeah, I'm gonna convert this recording and post it as soon as I can. So I'll talk to you guys later. Bye.